find like a perpendicular of a vector without having like part of the other vector already? Like I know how to find it using the dot product if there's only like one variable.
Talking about the one from the review.
No,
No,
like you're
not
given
that.
a plane and
So if
Right.
you, actually, say it again.
Okay, I'll find an example. You can ask another question.
Did you have, Macy, you want to clarify?
I do, let me find it. 25.
Okay, what's 25 actually?
Give me a second and I will find it. Not on top of it today. Oh yes, I remember this one. Okay, plane. There's a picture. Plane M1 has equation A1 of x plus B1y plus C1z equals D1. Yep. Plane M2 has equation A2x plus B2y plus C2z equals D2. Explain why in the diagram theta equals alpha, and then there's a diagram.
Okay. Oh yeah, that's crazy to look at it. So we want the angle between the normal vectors compared to the angle between the planes. Is that right? The relationship between those? And good luck with me drawing this, right? So we have one plane over here, say M1, and it's got its normal vector to that plane. Then we're going to have some other plane. You really have to test your visualization skills here. And then it's got a vector there that's normal to it. Does that sort of look like?
Yeah, and then the vectors intersect.
Yeah.
And that's
So so you got a plane here, and you got a plane there.
Oh, yeah, you're pretty. You're
Not too bad. It's one of my better ones there. So then, if we extend, these vectors can be any length we want. So then, this angle here, I think they're calling that alpha. And then we want to know how does that compare to this angle between, am I getting this right, Macy? That they're going to call beta? No.
That is kind of what it looks like. Do you want to look at it again?
Yeah, better.
Not really sure what it's referring to. Is that what it just said?
Yeah, I think that's what it's trying to say. So it's like drawing, and trying to do a better job. So they're kind of like showing a line in this plane, and then a line in this plane. So you can't see what was blocked there, but that's still the same angle beta. That's what I intended. That's the angle between the planes. Does that kind of make sense?
I believe so.
Yeah, and then they try to ask us how are alpha and beta related to each other?
No, it's just why are they the same?
Why are they the same? So we can see, so this angle here, like if I move this line over so that it's part of this vector here, and then likewise this line there, then what we get is really a quadrilateral where, this is the normal vector to that one plane, and that's the normal vector to the other plane. Can you see that, Rebecca? Are you okay? So now when you look at this, so we're looking at, and remember, this is our angle beta in here. So it's not the angle that's part of the quadrilateral. So let's see what we know. We know that these are normal vectors, so they're each 90 degrees. It's a 1, 2, 3, a quadrilateral, 4 sides. So you can see that if you divide it into 2 triangles, the sum of the angles in each triangle is 180. So we got 360 for the whole quadrilateral. Well, 90 and 90, 180, but it's accounted for by those 2 angles. What's left is 180 for these 2 to share. So alpha is one of those angles. So that means that this angle, and I need more colors. So, yeah, so this angle right here, so this angle right there that's in that quadrilateral, you with me? Alpha and that angle have to add up to be 180. That's what's left of the 360 after we get rid of the 290s. So these two angles are supplementary. They add up to be 180, Rebecca. Okay. Now, when you look at this yellow angle here and our beta, they make up that straight line. So they have to add up to be 180 as well. Well, that means the alpha and the beta must be the same. So the takeaway is, what they want you to take away from all this is, if you want to know what the angle is between two planes, which is a hard idea when you think about it, it's like, oh, it's just the angle between the two normal vectors.
Okay.
We have tools to do that, right? We do the dot product. You get the cosine of that angle.
Yeah,
And so then that's what
explain why cosine theta equals cosine alpha equals A1, B1, C1 times A2, B2, C2.
Which makes sense now, right?
Yeah.
Because that's exactly how we find the cosine between those two vectors.
Makes sense, okay.
Okay, good. Oh, she got more, Macy.
Well, you never answered mine.
Oh, what was your question?
Yeah, we were coming back to her.
Oh, we were coming back.
Okay, I found an example.
Oh, yeah.
Okay. So it says, given plane M with equation 4x plus y minus 3z equals 10. And then you have to find the equation of a plane perpendicular to M.
A plane perpendicular to M.
Yeah.
So let's think about kind of the same story with these normal vectors are the key, because they act like slope of a line. They tell us how we're tilted. So the normal vector, this is plane M. So I'm going to say little m. I'm just making up this. Now its normal vector is going to be 4, 1, negative 3. Right? That's perpendicular to there. So if I want a plane perpendicular to this plane, I need a normal vector that's perpendicular to this normal vector.
Wait, when you say normal vector?
Normal vector means perpendicular to the plane.
Oh, okay.
So,
yep, okay.
Okay, so you got a plane, and this vector that's perpendicular we call a normal vector to the plane.
Yep, okay.
Okay?
Makes sense.
Yeah, the vocabulary language is just daunting when you're starting out in any math class. Okay, so far. So,
now this is where I get lost. How do you find it?
well, so first let's find, there's lots of opportunities here, right?
Yeah.
So, shall we find so this is M. I'm going to call this, here's our new vector. I think I can do this.
I thought it was going to be easy. There's a lot of questions like this.
I think so. So we're going to make some of the dot product with this as 0. You ready?
Can we just like make up numbers?
Yeah, we can make up numbers. I love it. What are you feeling, Macy, the makeup queen? What do you want to call it?
I don't want the responsibility.
Oh, too much responsibility.
I might take that.
Okay, you'll take that.
Part 2, okay. Negative, wait, no, I'm thinking addition. Okay, but
How about -1? I'll get you started.
-1, -3, or -4. Does that work?
Yeah.
I don't know, but I don't think that'll work.
Sure. You got it to be 0, right?
Yeah.
-4. Oh, now, how about +4?
Yeah.
Now what?
Oh, I forgot about to do that. So wait, we just like made that up and then that was the answer?
Well, no, we're not done. Now that's just a normal vector to a plane.
We just fabricated vector.
Yeah. Now, let's see, do we have to do anything more? Plane perpendicular.
Well, we have to, yeah, find
I
that.
think we have to, I don't think we even done that.
Don't we have to find the plane?
I think it could be any point, right? Because if our plane is perpendicular, so there's our plane right there, that's the And our plane is going to be perpendicular. So we just came up with a vector perpendicular to that one. So I don't think it really much matters, because we could pick a point right here, right, in this plane, but if we moved it back a little bit, it's still going to be a perpendicular plane. So I don't think it much matters what we use as
So
a
we just
point,
pick any
any
point?
point you want.
So
I mean-
like the D could be whatever number
You
you
can
want?
put whatever you want in for D. So you can say negative x plus 4y equals, what's your uniform number?
18.
Got a good feeling about 18. Okay? I think that's going to work. Right? Because, well, I mean, these planes are perpendicular because their dot products are 0. That's how you built it. And it's a plane. It doesn't really matter where it contains the point. Is that okay?
That was like.
It's not always that easy, but this one is. Okay?
I got one question.
Yeah.
37. Same. Yeah.
You're hoping somebody would ask you a question for you. What's 37?
It says the purpose of this exercise is to find the distance between the point 3, 1, 5 and the plane 2x plus 2y plus z equals 4.
2x plus 2y plus z equals
4. And then part A says find a vector equation of the line that contains 3, 1, 5 and is perpendicular to the plane 2x plus 2y plus z equals 4. So we're just finding the perpendicular vector for that one.
So we want, say it again, so we want to,
Vector through that point perpendicular to that point. So I think that I can do that part.
okay, I think we can do that, okay.
And then part B says where does the
Wait,
line?
does everybody else need the part A? Is that clear?
It wants what?
It just wants the perpendicular vector that goes through that point. Right?
Is it a line or a vector that it wants?
The vector equation of the line.
So vector equation of the line. So this is going to give us our direction vector right here. This 2, 2, 1 is our direction vector.
Yeah.
And we want to go through that point, so that's like our starting point. And so we'll just say there's our vector equation for the line through this point, perpendicular to that plane. Amy, okay?
Yeah.
Okay.
Part B says where does the line intersect the plane?
Where does the line intersect the plane?
That's where it got lost. Yeah, that's
So
where I got
that gets
it.
tougher, right? So what we want then is to know where this line intersects this plane. So that means what I think we need to do is from here, we can say x is equal to 3 plus 2t. You with me there? Karen? And y is going to be 1 plus 2t. And z is going to be 5 plus t. So that still holds all that information from our line. And then we're going to plug this in for x, that in for y, that in for z. That'll give us a value of t. So in a sense, when this line or a particle running along that line is going to hit the plane. And once we know that t, we'll come back and plug that t in here and recombine them, or we can do it here either way. And that's going to give us our x, y, z points on the plane. Does that make sense? Want me to do it?
Yeah, better do it.
Okay. So we are going to say that we have 2 times 3 plus 2t plus 2 times 1 plus 2t plus 5 plus t equals 4. See where I've done that? Okay. AC in the corner, we okay? So So distributing 6 plus 4t plus 2 plus 4t plus 5 plus t equals 4. 4t, 4t, and t, I think is 9t. 6, 8, 13. Subtract it to the other side, and that's going to be, oh, we must be on the right track. Works out that nice.
Love it when it works.
I had a professor in graduate school, he said, the answer is always 1, 0, or -1. You just keep working until you can get that. Okay? So now that we know what t is, now we can find the point. You can either use the green, or you can go back and, I think the green might be a little easier because it's a little more direct. So that means our point is going to be 3 plus 2 times -1 is 3 plus -2 is 1. 1 plus 2 times -1 is 1 minus 2 is -1. 5 plus -1 is 4. I think that is our point of intersection between our line and that point.
Okay, and then there's also part C.
So,
I'm sorry. Part C, find the distance between 315 and your answer.
so now I want the distance between 3, 1, 5 and our 1, -1, 4.
So is that just the,
It's the distance formula in 3 dimensions.
Okay.
So it's going to be Pythagorean. Right, so you get the square root of subtract the x coordinate squared plus subtract the y coordinate squared plus subtract the z coordinate squared. No matter what order you go in because you're going to square them. So we go 3 minus 1 squared, 1 minus -1 squared, 5 minus 4 squared. You with me on that? Kent, what are you doing?
Reading.
That's not even a math book that you're reading.
If I had a math book, I might have to read that. Probably as interesting as this book.
2 squared is 4. 2 squared is another 4. Oh! Boy, somebody put a lot of time and trouble into these problems.
okay, thank you.
Okay, we good to go? All right. So we're going to talk today about determinants. All we're going to try to do today is to learn how to find a determinant. What we actually want to use these for, we'll have to wait till tomorrow.
Some of us just don't want to use them in general, I'm guessing.
Well, I'm guessing you're going to want to use them in the next week or two here anyway. So we're going to have to learn some new kind of vocabulary and symbolism here. So when we talk about, so I'm going to say we have A1, A2, B1, B2. So when we arrange those in an array, then we refer to these are rows and these are columns. So rows go horizontally, columns go vertically. Now, we are just going to scratch the surface on what you can do with this. I mean, you can take many undergraduate and graduate level classes on linear algebra, matrix theory, all that stuff. It's all related to what we're doing here. We're just talking about just a little bit. So we're just getting a taste of what this is about. So if you take these arrays of numbers, then you can, if you put these little square corner thing brackets on them, then it's okay to talk about that as what's called a matrix. So that's known as a matrix. Ooh, a cool movie made about the matrix, huh? So we have this we would say is a 2-row. We always go, when we talk about these, we go rows by columns. So these are dimensions of a matrix. So this is a 2 by 2 matrix, 2-row by 2-column matrix. Now matrices, that's the plural of matrix, can be any dimensions. They don't have to be what we call square, 2 by 2, 3 by 3, 4 by 4. They can be 2 by 3, 5 by 2, or whatever you want to be, okay? What we're going to talk about, determinants, require these to come from square matrices. So determinants always apply to things that have the same rows, arrays that have the same number of rows and columns. 2 by 2, 3 by 3, 4 by 4, 5 by 5. We can't take the determinant of a 2 by 3 matrix. It's just not defined. So ours will always be, we say square. Same number of rows as columns.
Two questions that are semi-related. Why is it matrices and not matriae? And how do you spell matrices?
So I was not in the room when they decided how they are going to spell this or say it, but that's matrices. So the plural of matrix is matrices. I don't know. I think that's more about English language. That's beyond my scope of expertise by a long shot. Okay. Sorry, that's all I got. Okay? So what we're going to do now, so what it turns out that what matrix has these little square corners, determinants. So I call that matrix A. Then we could talk about the determinant of this matrix. And sometimes you'll see it written as DETA, short for determinant. But the symbol that denotes it as a determinant looks like a big absolute value sign, but that's, we don't call it an absolute value sign in this context. So when you see these straight line symbols around this array of numbers, that's understood to be a determinant. So that is the determinant of a matrix A, or determinant of A, or a determinant. It is always a number. A determinant gives you a number. And the number that you get in the 2 by 2 case is you multiply down the diagonal, so that's A1 times B2 minus what you get by going up the diagonal, B1, A2. So it's down minus up in a 2 by 2 determinant. So, for example, if we had, say, 5, 3, 2, negative 7, and we want to evaluate that determinant, then we go down, so that's 5 times negative 7 minus 2 times 3. And so in this case, that's negative 35 minus 6. Right, so I'm going to get negative 41. Does that sound right? Now what that means we'll talk about later, and not right now, but that's just how you evaluate a 2 by 2 determinant. If only life was always that simple and straightforward. It's not. So we move on up to 3 by 3 determinants. And things get more complex. So a 3 by 3 determinant might be something like A1, A2, A3, B1, B2, B3, C1, C2, C3, straight line symbols on the outside to denote that. So we are going to find 2 ways to evaluate 3 by 3s. 2 ways to evaluate. One of them is really clever and works only for 3 by 3s, just like what we just did there, the down minus up. That only works for a 2 by 2 determinant. So I'm going to show you first the way that only works for 3 by 3s. After we do that, we'll talk about a way that generalizes to evaluate any determinant, in particular, the way that you evaluate determinants that are bigger than 3 by 3s, because there's no more clever tricks. There's a clever, 2 by 2 where you go down minus up. There's going to be the clever 3 by 3 where you go down, plus down, plus down, minus up, minus up, minus up. After that, we got no more tricks, no more cleverness to go around. So here's the idea that we're going to do. So this is method 1 for evaluating 3 by 3s. And I'm going to say only works for 3 by 3 determinants. So don't get carried away and try to do this somewhere else. It's not going to work. So let's look at, I'm going to go by rows, 5, 2, 8. You take a little time to make these neat and organized, because otherwise you're making your life way more difficult. Kent, you might want to ask if somebody else would write it down for you there. I'm just messing with you. 3, 4, 7, negative 1, 6. So here's our determinant. And here's where having like graph paper can help too, because you put a number in its own little box. Now, what I'm gonna do is I'm gonna recopy the first two rows right next to this. I try to keep your spacing and everything neat and organized. So 5, 3, 7. This is recopied column 1, sorry, I think I said rows. Column 1, and then column 2. 2, 4, -1. Okay? Now, sort of like what we did in the 2x2 case, but way, way more messy, we're going to multiply down the diagonals, and we're going to multiply the 3 terms that we hit, and we're going to add those results together. Then we're going to come back and go up the diagonals, multiplying the 3 terms that we hit, and subtracting those results. So it's going to be down, plus down, plus down, minus up, minus up, minus up. So I'm going to go down this diagonal. So that's going to be 5 times 4. I'm going to write it all out here just so you can see where it's coming from. We're not going to do this all the time, writing it all out. Plus, because we're going down, then we're going to go 2, 1, 7. This is why, you know, having a little organization in legible handwriting goes a long way, and not can be a real detriment. Then we'll go 8, 3, -1. So plus 8 times 3 times -1. Okay, now I'm going to add these, but we're not done. This is only part of it. So let's see, 5 times 4 is 20 times 6 is 120. That sound right? 2 times 1 times 7 is going to be 14. 8, 3, and -1 is a -24. So let's see, 14 and -24 is -10. -10 and 120 is 110. But we're going to have to get some more. So now we're going to go up the diagonal. Same thing.
Out of colors.
See? Something you said for chalk here, huh? So 7, 4, 8. 7 times 4 times 8 minus, because we're going up the diagonal. -1 times 1 times 5. Minus, because we're going up the diagonal. 6, 3, 2. 6, 3, 2. It's a lot of arithmetic.
What about 3?
What about 3?
It's the only number we haven't hit.
And 4.
But they've all been in there somewhere, right? Because that 3 we recopied over here. It's included. And that 4 was over there. So I mean, there's other ways you can write to do this, like if you're going to computer program it or something, but this is the way it's done by hand. Yeah, I know it seems weird, but we're getting all the numbers. They're all contributing.
he was included too.
Yeah, oh no, nobody's been left out here. This is all inclusive.
I'm 1 color short. This is unacceptable.
Wow. Okay, I'm trying to think of the way to see. 4 times 8 is 32. 32 is 210, and 14 is 224, is that right? Please don't take my word for that. See, we got a 1, 1, 5, so make that plus 5, minus 36. Let's see, 5 and -36 is -31. -31 and 24 is a -7, so that's going to be 193. Does that sound right? Yeah, thanks. So that's 200, 303. That's the value of our determinant. Okay. Katya, you all right?
Yeah, I thought when we went up, weren't those all negative?
Oh, yes. I left off the minus there.
Oh no.
Oh.
Unfortunately.
Okay, back to the drawing board. -224, -236 is -260.
I like the original.
-260 plus 5 is -255. It's minus, minus, minus. So that's going to be a -225 and a positive 193. Let's see, 7 would make that 200. 25 is -32.
Wait, wasn't
Wait,
it?
where'd the 193 come
Wait, was it, yeah, 193 is the last answer.
from?
It was 110, right?
110, yeah. Okay.
Thank you, Aiden. This nice to have somebody paying attention here. All right, this is my third try, all right? I'm gonna get this. Negative 225 and a positive 110 is gonna be a negative 115. I wrote the answer. 145, is that right?
Yeah.
Yes, that's good, because that's what I got when I did it, and I could think a lot of years ago. Okay, where are we with that? Okay, so and this is nice, and, I mean, it's not nice, but it works. So the third method, well, second method for 3x3s, but this is the general method for evaluating determinants of all orders. So I'm going to call this method 2. And this is the general method for all.
And I'm guessing it's method 2 because you don't use it unless you have to.
Say it again.
I'm guessing it's method 2 because you don't want to use it unless you're forced to.
I wouldn't say that. Well, we'll see. Even in a 3x3 case, if you get we'll see, if you get a determinant that's got a bunch of zeros in it, this can really be quick and efficient. So you'll have some choices about how you do this. But if you have anything bigger than a 3x3, you got no choice. This is all you got. So this is known as expansion by minors. So you have to have very young people do this. I'm just kidding. So before we can do this, we have to learn a few other little pieces here. We have associated with any determinant, there's a sign pattern that goes with the position in the determinant. So it always starts with the first term always gets a sign associated with it, a positive. And then from that point on, we alternate signs. So in the case of a 3x3 case, you would go plus, minus, plus. And then likewise, as we go down, we go minus, plus. And as we go back across, minus, plus, minus. And it always works out and it always alternates. So that would be the sign pattern. And we'll talk about how we're going to use this. We'll get to that in a minute. But just first, there's a sign that is associated with the position in the determinant. So if we have a 4x4 determinant, you would start always with plus, and then it would go minus, plus, minus. So we just alternate. And going down would be minus, plus, minus. And then as we fill in, going across that second row, plus, minus, plus. It always works out minus, plus, minus, plus, minus, plus. Okay? All right. So that's the sign pattern. Now, we'll hold off on when we're going to use that for a moment. Now, what we mean by a minor, so I'm going to fill out, let me put some numbers in here because it'll be easier to refer to it. I'm going to leave that there for a moment. So let's do an actual 3x3 determinant. And we'll do the same one, see if we can get the same answer. Hope it doesn't take 3 tries on this one. Was it 5, 2, 8? Is that the same one we have?
Yeah.
And 3, 4, 1. And 7, negative 1, 6. So each of these entries, so 5 is called an entry. It's the row 1, column 1 entry in that determinant. So you call them entries, and you can reference them by where they are. So the row 2, column 3 entry would be 1, and so on. So we will be able to choose to expand along any row or any column that we wish. Okay, so to start with, we're going to assume we're going to expand along row 1. So as we expand along row 1, we will use the sign pattern only for the row or column that we expand along. So we would, in the back of our mind, be saying we have plus, minus, and plus. Now, a minor is, since this is a 3x3 determinant, a minor is a 1 order smaller determinant. So from 3x3, we're going to go to 2x2. It is formed by crossing out the row and column that entry sits in. So 5's minor is when we cross out the row and column that 5 sits in, it's going to be 4, 1, negative 1, 6. That's considered the minor of 5, or the minor of that row 1, column 1 entry. So every element there, every entry there has its own minor. Now we're only going to use the minors of the row or column that we choose to expand along. And crazily enough, we get the same answer no matter what row or column we expand along. So let's just, for the sake of argument, expand along row 1. So what we do is we take that entry 5 and we multiply it, and it would be the positive 5. So it means keep the same sign of that 5. So if that 5 had been a negative 5, we would have gotten a negative 5 here. It just means that you don't change the sign there. So it's that entry, 5, times its minor. So that's the 4, 1, negative 1, 6, writing it down by rows. Then we're going to go, because from the sign pattern, which we only use along the row or column that we're expanding along, it's going to go minus whatever that entry is in the row 1, column 2 spot. So it's a minus 2. And had that 2 been negative, would have made it into a minus negative, made it a positive 2. So it's a minus 2 times 2's minor. So now you imagine, you're deleting the row and the column that 2 is in, and you keep the numbers that survive. So in this case, 3, 1, 7, 6. 3, 1, 7, 6. You with me there? And we continue expanding. Now it's back to a plus, so we keep the same sign of that entry. Happens to be a positive 8, so it'll be a plus 8 times its minor. And we delete the row and the column that 8 is in, leaving behind 3, 4, 7, negative 1. So 3, 4, 7, negative 1. Now we're in home free. I mean, we have a ton of arithmetic to do, but there's no more big concept. 2 by 2s we can do. So it's 5 times, that's 24, minus negative 1. You with me now? I'm going down, minus up. That's how we do 2 by 2s. Yeah, we okay? Then you got a minus 2, and then we're going to go down, minus up. 3 times 6 is 18, minus 7 times 1 is 7. I'll come back to those. Plus 8, and then negative 3 minus 28. Just a ton of arithmetic. So that's going to be 24 minus negative 24. 25 times 5 is 625. 18 minus 7 is 11. Times negative 2 is a minus 22. So a negative 31 times 8. 230 would be 240. So negative 248. That sound right?
Why is it a negative 28? Oh, never mind, just kidding.
Because it's minus up. Okay. So let's see, the 22 and the 248 that are both negative, that's going to be 260, 270. All right. 270. Oh, gonna get there, I think. 200 from 600 is 400. No, not quite that. So 300. Not gonna work, is it? What do we got? 55. Did I do that right? I got 355. Is that
That's
right?
what I got to.
What did I do wrong? Oh, because 25 times 5 is 125. Come on, guys. Supposed to be helping me.
You seem so confident.
Okay, let's try this again. Now I think we're going to get negative 145. What do you guys know? You'll think whatever I say it is. Okay? There you have it. So, now if I ask you to do a 4 by 4 or a 5 by 5, which I probably will, it will probably be full of zeros. Because if we had there been some zeros here, if we expand along a row or a column that's got a bunch of zeros, we would get, say that was a 0, we would get 0 times its minor. Well, that's 0, you don't have to do that work. So the more zeros you have, the quicker and easier it is to evaluate it. And so you choose the row or column with the most zeros. Now, that's the good news. The bad news is, here, in the case of a 3 by 3, we end up evaluating 3 2 by 2 determinants. In the case of a 4 by 4, what size are the minors going to be? 3 by 3s. And how many are we going to have to evaluate? Or 3 by 3s, unless there's a lot of zeros. So it blows up quick. Okay, so let's talk about, so what happens when we switch rows and columns? This is kind of a, how are you going to, oh, great shape. Unbelievable. So suppose we take a 3, 2, 5, 7, 2 by 2. And let's evaluate that. So I'll let you do it, give you a moment, and then we'll see if we agree. We had 11. So let's see if we switch a row. So I just moved the 3, 2 to the bottom and the 5, 7 to the top. Now evaluate that. You change the sign, right? That's always true. Switch a row or a column and it changes a sign. Okay, interesting fact about determinants. What if we multiply by some number k? So I'll go back to 3, 2, 5, 7. So what we do is we bring that into our determinant. We multiply a determinant by k or a matrix by k. It multiplies every entry in there by that. So that's going to become 3k, 2k, 5k, and 7k. Sounds like a cross-country marathon. So, okay. So we go down minus up. So down we get 21k squared minus 10k squared is 11k squared. So curiously enough, multiplying the matrix by a constant multiplies the determinant by the square of that constant. Okay? Another fact, if you take a determinant, say I go 3, 5, and you pick as a row, or you could do this with columns too. You took a multiple of 3, 5, say 6, 10. Now if you multiply there, or evaluate the determinants, we get 0. That's not a coincidence. It's always true. So if any rows or columns are multiples of each other, the determinant's going to be 0. There's a lot of theory lurking behind all this that we aren't going to get into here, but you would if you were in a linear algebra or a matrix theory class.
So that both the rows and the columns all have to be like multiples of something or another in the same row and column?
Well, I just started with 3, 5 and multiplied that row by 2 to get this one. But if I had gone, suppose I'd said, we have 2, negative 3, and I multiplied this column by, say, 3, so 6, negative 9. So if 2 columns are multiples of each other, they're still going to be 0.
Okay.
So we're going to get negative 18 minus a negative 18. So any rows or columns that are multiples of each other, the whole thing's going to be 0.
Okay.
And that would be true no matter what the size is. So if I had a 10 by 10 determinant, oh God, it would be awful. But if any 2 of those rows are multiples of each other, that whole determinant is going to be 0.
Wait, the whole thing?
The whole thing is going to be 0.
That's
Yeah,
nice. And
kinda
it's only if, so like there's 10 rows, so 2 of the rows are the same, the whole thing.
Or
is
2 of the
0.
columns.
Or 2 of the columns.
But it can't be a column and a row?
No.
Oh, okay.
But what's crazy, and we won't get into this, you could even say, if you had that 10 by 10, if one row was a linear combination of the other rows. If you said, if I go 2 times this row, plus negative 3 times that row, plus that row, and it equals this row, the whole thing's 0. There's some stuff going on there. So, we aren't going to get into, but there's reasons for that. So often these are thought of as, we're talking about vectors. So these are built, you can think of these as built, constructed of either column vectors or row vectors. So you could think of, 3, 6 as being a vector, or 6, 10 as being a vector, either way. And these have meaning there. Not that we're going to get into that. That's good for us. I got through what I wanted to do. So I'm going to start, because I have the gift of time, on some of the application stuff, because that may take a little bit longer tomorrow. So I'll start on it today, and then we'll pick up in tomorrow's lecture where I leave off here today. Okay? So this is now 12.8 applications of determinants. So the first one is known as Kramer's rule. We used to teach this in algebra 2, but I haven't done that for a long time. So Kramer's rule is a way of using determinants to solve a system of equations. And this is not the greatest application of determinants in the world because you see how much work a determinant gets to be once it starts getting bigger. So there are better ways of solving systems of equations than Kramer's rule. So 3x plus 4y equals 7. Remember doing this in your algebra 2 days? Yes is the correct answer. And 11. I made this one have kind of messy answers just because then at least Kramer's rule seems like it has some kind of use. So we have this, and so you know that we could do substitution or elimination, I think you call it, where you multiply these rows by something, add them together to get rid of one of the variables. Just nod your head, it'll make me feel better. Thank you. Okay, so another way of doing this is with determinants, and that's called Kramer's rule. So I'm going to call D is known as the determinant of coefficients. So what we do now, to do this, we want all the x and y's on the same side of the equal sign in the right order, so that the x terms line up with the y terms, and then the constants on the other side. So if this didn't have a y term, well, it'd be really easy to solve. We wouldn't be doing Kramer's rule anyway, but it would theoretically be 3x plus 0y equals 7. So if we just look at the left side, make the x, y's disappear. Their coefficients form a 2 by 2 determinant. 3, 4, 4, 9. Okay? So that, you can see the row 1 is the first equation, row 2 is the second equation, with kind of just the essentials, right? We don't need those placeholders. We know that's the x coefficient, y coefficient by where it is. We see the x coefficients in column 1 and the y coefficients in column 2. We'll get back to that. Then we create a new determinant we call d sub x. D sub x we construct by starting with our determinant of coefficients and then replacing the x column by the constants on the right side. So replace the x column by the right-hand side. So that's going to become 7, 11 becomes now the first column. We threw out the x coefficients. The y coefficients stay there, 4, 9. That's dx. Then we create another 2 by 2, d sub y. And that, we're going to again go back to starting with determinant of coefficients. This time, we're going to replace the y column by the right-hand side. So the first column of the determinant of coefficients stays 3, 4. The x's are back in. The y's get tossed. We put the 7 and the 11 in their place. Does that make sense? So the claim is, what Kramer's rule says is that, if these intersect, they're going to have an ordered pair x, y. There's a point of intersection of those two lines. The x is going to be dx over d. That is, you can evaluate that 2 by 2 determinant d sub x divided by the 2 by 2 determinant d, and that'll give you the x coordinate. And the y coordinate Is dy over d? Let's do that. So, d is, this is where I wait for you to say something.
11.
And that's showing me 11. Okay, see, I've been struggling all day trying to get this arithmetic. You guys are there while I'm still trying to think what to say to multiply. Okay, so d sub x is going to be 17 according to Katya. We're going to trust her on that, just like.
Wait, no, it'd be 19.
Oh, trust but verify, huh? Well, 19. Nobody said anything when I offered it up. Okay, let's see, 33 minus 28. Even I can do that one. 5? So we're going to then get that our point of intersection, so x is going to be, what did we say, dx? So that's going to be 19 over 11. And the y is going to be 5 over 11. Kind of crazy?
Yeah.
Now, when you have two lines, one thing that can happen is they can intersect in a single point, and there's the coordinates of that point. What else could happen? They could be parallel, no solution at all. And what's the third thing that could happen? They could be coincident, be the same line, get an infinite number of solutions. You can tell what's happening from Kramer's rule, from these determinants. If d is equal to 0, so d is equal to 0, now we're in trouble, right? Because now we're trying to divide by 0. So that tells us that we are not going to get a single point of intersection. These are not intersecting lines. They are either parallel or coincident. So then if you evaluate any one of the others, dx or dy, if that is also 0, then those two things together mean we have coincident lines. So it will tell you what's going on. Now, if d is 0, but the dx is not 0, that means we're going to get parallel lines. So it will tell you, you can tell through the process of using Kramer's rule what exactly has happened. Now you can do this in three equations, 3 unknowns as well. But I think the interest wanes because how many 3 by 3 determinants are you going to have to evaluate? So now imagine you have x, y, z, x, y, z, x, y, z. D is going to, the determinant of coefficients is going to be 3 by 3. So will dx, so will dy, so will dz. So you're going to have to evaluate 4 3 by 3 determinants. Pretty soon you're like, there must be a better way. And there are. It's not a very efficient way to do it. Very good.
Yeah, I wonder if we're going to program it.